right, well, let's get started. Very good. I see we were learning. The cameras are coming on. Oh, I don't have any paper. Hold on one second. Let me get some paper. All right, sorry about that. Okay. So, just a couple of announcements. We'll be finishing up chapter 6 today. So the torsion chapter. And then, so the second exam, which is on that last bit of the axial and the torsion is going to be a week from today. So next Tuesday. So Thursday, again, I'll just do new problems. So no new material. And so the second, the exam will be pretty similar in format to the first exam. Obviously, content's a little bit different. So, right. So today we're going to just cover angle at twist and statically indeterminate problems in torsion. Okay. Is there any questions?
4 and 5? Is 5 torsion, or is that 6?
Chapter 5 is torsion, right? Chapter 4 is axial, right? So yeah.
Yes. Okay, and is it going to go over chapter 3, or is that just like the concepts we needed to learn?
Chapter 3. Oh, well, yeah, no, it'll be in, yeah, that's right. I'm sorry. That's right. We didn't do chapter 3 on the first exam, right? We just got up to strain. That's right. So yeah, so it's going to be chapter 3, 4, and 5. Okay.
Okay. Thank you.
Right. Any other questions? We got a chat. 3, 4, 5. Yep. Okay. All right. So if there aren't any questions, then let's get started on material I wanted to cover today. So I basically want to do mostly problems today. So, but I do want to cover got one thing to cover. Actually, 2 things to cover. I have 2 things to cover. So, where's my share thing? Share. All right, let me do this real quick. So I didn't cover this explicitly last time. This is pretty straightforward, and most likely you've seen something similar to this. So you can see my slides now, I'm hoping. So when we're talking about torsion, one of the big applications of torsion in mechanics materials is for analyzing shafts that transmit power, right? So if you remember when we were doing torsion, the objective, right, is to figure out the stress, which is the torque times the radius over this geometric factor J, okay? And a lot of times you'll see problems where they, instead of giving you the torque, T, they are going to give you the power, P, and the angular speed, or usually they give it as an angular frequency, omega, right? So a lot of times you're going to see the power given in horsepower or watts. And then for the angular speed, which I'll call it as a frequency, you'll see it as like revolutions per minute or revolutions per second or something like that. Okay. So obviously, if you remember from physics 1, the power is equal to the torque times the angular speed. But this angular speed, the units of this need to be radians per time, like radians per second. And if that's the case, and then the torque is in, let's say, pounds and then inches, right? Then that means the unit of power you would expect wouldn't be horsepower, but pound inch per second. All right. So we have to be a little bit careful about the units. Very often, you won't get it in terms of that, right? So, obviously, if they give you the power and then the angular speed, you can then get the torque using the following relationship, the power over the angular speed. But we want to be careful about the units, right? So if you're given a unit of horsepower for the power, there's no way to derive this. It just is what it is. It's 550 pound-feet per second, or probably more useful for us because we tend to use inches, 6,600 pound-inches per second. So if you're told that you have a motor with 2 horsepower, that means it's going to be 13,000 pound-inches per second, right? And likewise, if they give you the frequency that the shaft rotates in terms of revolutions per minute, RPM, now you remember there's 2 pi radians per revolution, and then there's 60 seconds in a minute. So that would give us, 2 pi over 60 radians per second, or 1 RPM is pi over 30 radians per second, right? So, just as a super simple example, right? If you have a shaft that transmits 3 horsepower of power, and it rotates at 600 RPM, what is the torque in that shaft, right? So we know that the torque, right, is the power over the angular speed. So we got to do the unit conversion, right? So the power is 3 horsepower. So we multiply 3 by 6,600 pound-inches per second per horsepower. That gives me an equivalent power of 19.8 kip inches per second, right? All right. Now, similarly, we have to go from RPM to radians per second, right? So we have 600 RPM, and then we modify that, we multiply by the factor pi over 30, and that gives us radians per second, or 62.8 radians per second, right? And then these numbers, we can plug into here, and that gives us the torque, right? So you can see the seconds cancel out. Radians are dimensionless, and this gives us a torque of 315 pound-inches, okay? If you're in SI units, right, the power will most likely be in watts, or very often actually kilowatts, right? And remember, a watt is a joule per second, or a Newton times a meter per second, right? So, that's the units you'll have there. So if you got kilowatts, you'll probably get your force in kilonewton meters, right? And then also you still have to change from RPM to radians per second for SI, obviously, right? That's not an SI thing, okay? So not a big deal. Watch the units. If they give you a power and a frequency, that means you know the torque, okay? So that's basically it, right? So the two mean the same thing, right? Either you're given a torque or you're given a power and a frequency, and you can figure that out, right? It's kind of like the same thing as I can give you an allowable stress, or I can give you a failure stress and a factor of safety, right? You can calculate those off of that, all right? Okay. All right, the second thing, a little bit derivational, but I can do this relatively quickly, is the angular twist. So when we did the axial stuff in chapter 4, right? Remember, we figured out how to determine the elongation of the axial member, right? The elongation delta L is the force times the length over the cross-sectional area times Young's modulus, right? So we're going to come up with a similar relationship for torsion, right? Something that's going to hopefully rate the applied torque to the amount of twist phi through the geometric and the material properties. Okay. So last time we, we derived the fact that the shear strain, gamma, was equal to the radius times this d phi dx, how much the angle of twist changes with respect to x. And we got that from, this similarity triangle here, okay? So if you look at something like that, then we can rewrite this as follows, right? We can write that gamma over rho dx equals d phi. And so from that, if we were to integrate both sides, that would give us d phi, right? If we were to integrate both sides, on the right-hand side, we would get the total angle of twist phi from, say, 0 to L. Very similar to what we did for elongation, okay? So that's fine, but we need to work this a little bit. So let's take this term here, okay? And let's just kind of tweak that a bit. I'm gonna go down here, I guess. So the shear strain over rho, let's look at that term, okay? So the shear strain, I can replace using Hooke's law for shear as the shear stress tau over the shear modulus G. So that's going to give me tau, the shear stress, over rho times the shear modulus G. All right, that's good. But also, we remember that we can get the shear stress in terms of the torque, right? So the shear stress is the applied torque times the radius over that geometric factor J, right? The second polar area moment, right? And in that case, this now becomes T rho over rho J G, and obviously the rho's cancel out. And then we can put that back into here, and we can get that the total angle of twist equals the integral from 0 to L of T over J G d phi. And if you recall, when we did the axial problems in chapter 4, we got that the elongation delta was the integral from 0 to L of the force, the internal force, N over A E dx. And you can see the similarity here, right? Instead of the internal force, we have the internal torque, T. Instead of the geometric factor, A, the cross-sectional area, we have the geometric factor, J, the second polar area moment. And then instead of the material stiffness for axial problems, Young's modulus, E, we have the material stiffness for torsion, the shear modulus, J, I mean, sorry, not J, G, right? And so we have the same thing, okay? So very similar, very similar. And then also, so, whoops. Oh, so the angle of twist is the integral from 0 to L of the torque over J times G dx. So just like when we had the axial problems, right? In the axial problems, things were simplified by, if we had sections where the torque, or in that case, the force and the area were all constant, right? Let me just approve this request. Okay. So if we have a section, right? Like a shaft with a torque T applied onto it and a constant radius, constant shear modulus, and of some length L, right? All these terms are constant in the integral. They come out, and we just get T over J G integral dx. And this is just going to go to the length. So we get that the angle of twist is the torque times the length of the shaft over J times G. All right. So again, it's totally analogous to when we did the axial problems. Right. So if you remember PL on AE or NL on AE, right? You can easily remember from the analogs what the angle of twist is, right? So if we have a problem like this, where we're given, the torque, the geometry, so we can figure out J, and the material property, so we know G, and obviously the length, right? You can then figure out how much this front face twists relative to the back face, okay? The angle of twist. And so that's the way it works. So we're going to do the same stuff with angle of twist that we did with elongation, right? So if you have torque applied onto like a stepped shaft, right, where maybe there's a torque applied here and another torque applied here and a torque applied here, right? You can figure out the angle of twist of this section and the angle of twist of the second section using that equation, because T, J, and G are going to be constant in all those sections. And then to get the total angle of twist, you would just add those together, right? And this will also allow us to do the statically indeterminate problems. Because remember, when we had the statically indeterminate problems in axial case, we needed a extra equation, and it was always some sort of compatibility condition. In the axial problems, it was like that. The total elongation is 0. In this case, like if we had a torsional problem and it's fixed at the ends, right? And let's call this point A, point B, and point C. So this is A relative to B, and this is C, B, relative to C, right? If this is the case, right, we don't know the reaction torque at C or the reaction torque at A. We can only write that the reaction torque at C plus the reaction torque at A plus this known torque here, T, equals 0, but I have 2 unknowns. So I need an extra equation. The equation I'm going to use is that the angle of twist of A relative to C, which equals the angle of twist of A relative to B, plus the angle of twist of B relative to C. That has to equal 0. And that'll give me another equation that'll allow me to solve this torsional statically indeterminate problem, the exact same way we did it with the axial, okay? All right. Any questions on that? I think it's talked enough. Probably time to start solving a handful of problems, okay? Okay. All right. Let's share. Okay, so let's do a problem. Let's first look at problem 547, okay? So this one's a pretty straightforward one, if I can find it. Okay. Yeah, well, this is not one too. But... Too many steps to do this. All right. So let's look at 547. Okay. So let's not do this one. This is just the related problem. So they give us this shaft with a constant solid shaft, constant outer diameter, 340 millimeters. Oh no, it's got an inner. Okay, so it does have a. Oh no, I'm sorry, it's hollow. Although the picture doesn't look hollow. That's really weird. Okay, fine. It's hollow. Okay, because it's got an outer diameter and an inner diameter. All right. And it tells me how much power is transmitted on that shaft and the rotation speed. So here it gives you the frequency because it's already in radians per second. And I've got the power output in megawatts, okay? And it wants me to figure out the torsional stress as well as the angle of twist, okay? So, in this particular case, right, we're going to have to figure out J. So let's just calculate J right off the bat. So J is pi over 32, the outer diameter to the fourth minus the inner diameter to the fourth, right? So that's 0.34 meters to the fourth minus 0.26 meters to the fourth. And that gives me a J equal to my calculator's going to die. All right, so that gives me 0.863 to the negative third meters to the fourth. Okay, so that's J. All right. All right. Now we need to know the torque both for figuring out that the shear stress is TC over J, as well as that the angle at twist is TL over JG. All right. It's a steel shaft, so we can look that up, and we know that I always forget what the heck it is, but G is about 90. Let me check. I have it written down here. Okay, G for steel is 80 gigapascals. Okay, 80 gigapascals. All right. So to get the torque, right, the torque is going to be the power over the angular speed, right? And they give us the power as 4.5 megawatts, right, over the angular speed, which is 20 radians per second. And so, remember the watts is going to have units of Newton meter per second. So this is going to give me an answer in Newton meters. Okay, so that gives me 225 kilonewton meters. Okay, so that's the actual torque applied there. All right, and now we can take that and put that into these two equations, and we can figure out the shear stress is the 225 kilonewton meters. The outer radius, so they give us the outer diameter of 340 millimeters. So the outer radius is going to be half of that, 170, right, millimeters. So that's 0.170 meters. And J is what we calculated here, the 0.863 0.63 to the minus third meters to the fourth. So this is going to give us an answer in kilopascals. And so that gives me actually 44.3 times 10 to the third kilopascals, or that's 44.3 megapascals. So that's going to tell me that the shear stress on the outer surface of this power shaft is 44.3 megapascals, okay? So now likewise, we can figure out the angle of twist, right? We know that the length is, what do they give us for the length? Oh, right, 60 meters long. It's 60 meters long, okay? So the angle of twist, and now again, this is all dimensionless, so the angle of twist is going to give you the angle in radians, right? So the torque is the 225 kilonewtons per meter, or kilonewton meters, excuse me. The length is 60 meters, and then J is the 0.863 to the minus 3 meters to the fourth. And then G is 80 to the ninth pascals, right? It's a gigapascal, right? Okay, so this gives me okay, that gives me 0.196 radians. Or if you want to get that in terms of degrees, right, there's 180 degrees per every pi radian. So you can multiply that by 180 over pi. And that is 11.2 degrees of twist. So, you know, the way this is shown here, right, the torque is being applied counterclockwise looking down at the shaft. So this face here is going to rotate 11 degrees relative to that back face. Okay. All right. Let's look at a more challenging problem. That one's kind of boring, but let's look at them. It's a little more. Any questions on that one before I clear it all out? Okay. So here we go. Let's look at 549. Okay. All right. So here we have a solid shaft, right? A solid steel shaft. And you've got torques applied at points A, B, C, and D. And they want us to figure out the angle of twist of B, the right end, with respect to A. So I'm going to be careful about getting the right signs of rotation on these, okay? Because it's going to be important when we do statically indeterminate problems. So I'm going to use the following convention. I'm going to call this the x-axis. And that means that using a right-handed rule, torques applied in a counterclockwise manner are positive, as well as rotations in that direction are positive, okay? A negative rotation would be a rotation counterclockwise looking down the x-axis, okay? And so we're just gonna, you could do something else, but that's what we're gonna do for now, okay? All right, so to get this, we need to figure out the angle of twist in shaft AC, the angle of twist in CD, and the angle of twist in DB, and add those all together. So the total angle of twist, oh, actually, they want us to get B relative to A, so we'll go the other, let's do the other one. B relative to A, okay? So, actually, maybe should we flip this? I mean, it doesn't really matter, but we'll just keep this. So that's going to be the angle of twist of B relative to D, how much this face rotates relative to this first gear, plus the angle of twist between the two gears, D to C, plus the angle of twist, of C relative to A, right? So maybe in this case, maybe we'll draw X in this direction just to make it a little easier, because that's the way we're kind of looking. At least that's the way the problem wants me to look. And if that's the case, then, that's the positive direction using the right-handed rule. Okay, so imagine you're looking down from point B down to point A, okay? All right, so for each one of these, we're gonna get the angle of twist is TL over JG. And this is steel again, so G is still the 80 gigapascals, right? And now J is going to be the same for all of them, right? It's solid. So J for all three sections is going to be the J for a 40 millimeter outer diameter, right? So pi over 32.04 meters to the fourth. And that's going to give me 0.251 to the minus sixth meters to the fourth, okay? So that's J. All right, okay. So obviously, the lengths are given here. So this is the length of section BD. Here's the length of DC, and here's the length of AC. What we really need to know is the internal torque in each one of those sections, okay? And again, don't make the mistake of just saying, okay, the internal torque in section DB is 400 Newton meters because that's what's applied at B. No, this is the internal torque in that section. So the only way to see that is to draw the free body diagram. So if we were to expose the internal torque in section DB by putting a cut there, right? We would see the following, okay? So that would, here's the cut side. Here's B. We have a torque going this direction here, 400 Newton meters, right? And that's obviously going to balance out the internal torque, right? So, if we use a right-handed rule, you don't have to do this, but just like when we did the axial problems, we always wanted to put the internal force in a normal direction. So for torsion, right, that's going to be a torque vector like this, or if you were to write it as the little archy torque, it's going to be this type of torque. So this is the internal torque in section BD. So let me write that. I'll just do that. Okay. And here you can see that torque BD is obviously equal to minus 400 Newton meters. In other words, it's really going the opposite direction. And that means that face B is going to rotate in that direction relative to the cut section, right? So, okay, so let's figure that out, right? So phi is now, here's the phi for B relative to D, right? So that's going to equal the internal torque, which is the minus 400 Newton meters, okay? The length is 0.6 meters, right? That's the length there. J is 0.251 to the minus 6 meters to the fourth. And then G is the 80 to the ninth pascals, right? Okay. So that's going to give me an answer in radians, right? Because upstairs I got Newton meters squared, and downstairs I've got Newton meters squared, right? All right, so that gives me a rotation of negative 0.0120 radians, okay? So in other words, let's look at this now, right? Let's get the sense correct. Well, clearly, like if you look down from B, right, the way this is drawn, B is gonna, well, let's do it this way. All right, so this is B and this is D. B is going to rotate in that direction, in the negative direction, right? The negative direction is there by the 0.012 radians, okay? You can also, it also makes sense because in this particular case, the torque is going in that direction. So you would imagine that face B is going to rotate in that clockwise direction, looking down X as drawn of 0.012 radians, okay? So there's a couple of ways you can deal with the bookkeeping. You can be good about the signs, or you can look at it physically, you know what I mean, and get the right direction from there. Probably not a bad idea to be able to do both, but you need to be able to do the bookkeeping to understand which direction it's rotating so that, you know, if in section CD it rotates in the other direction, you don't want to add those together, but you want to subtract those, okay? All right, so I'm going to break you into groups, and I want you to do the same process and figure out the rotation of D relative to C, as well as the angle of twist of C relative to A. And if you know those, you can add those two up with the minus 120 radians, and that's going to give you the total angle of twist, okay? All right. So any questions before I break you up into groups?
Professor,
Yes.
to find DC, do we use the 100 and 1,200 newtons to find the?
You have to draw the free body diagram and then figure out what the internal torque is. Always, okay?
Okay.
You have to draw so it's not like, don't guess which torque to apply, right? On the
Okay.
end ones, it does work out to be the ones that are applied, but in here, it won't be. So you don't just grab the nearest torque.
Okay.
You have to draw the free body diagram, okay? Always,
Right.
okay?
Thank you.
So, okay. Let's just wait a couple more seconds for everyone to get back here. All right, so let's look at this problem kind of quickly, okay? So I did a little bit on it, right? So we already got the hardest thing about this problem, honestly. Well, one thing is getting the right internal torques, okay, but that's not terribly difficult. The harder part is keeping track of which way the faces are rotating relative to each other. So in this problem, right, they want to know the rotation of face B relative to face A, okay? And we already looked at this for the first segment, right, between BD and, you know, since the torques are as applied here, right, in this free body diagram, there's the 400 Newton meter torque that wants to rotate face B in this direction relative to D, right? So we know that the rotation of B relative to D is going to be as shown here, okay? So like if my left hand is face D and my right hand is face B is going to rotate in this direction 0.012 radians. Or if you were to look at it down shaft B, it's rotating in the clockwise direction. That's a negative rotation, right? So it's going to be clockwise, right? Okay. Now, if we look at what's going on in section CD, the first thing we need to do is draw the free body diagram that's going to expose that internal torque, all right? So here's that free body diagram, right? Not well drawn, but we have point B and then point D, and then we cut it in such a manner that it exposes the internal torque CD. So we've got 400 Newton meters going in this direction, and then the 1200 Newton meters going in the opposite direction. So that means that to balance that out, the internal torque at CD, this is one of the downsides of doing this stuff online. If I could use my hands, it would be a lot easier. But the internal torque in section CD is going to be as shown here, right? It's going in, if you're looking down the x-axis from point B, it's going in the clockwise direction, okay? All right. So there's kind of two ways to do that. One way to do it is to keep really good track of the signs, okay? The other way to do it is to just physically kind of figure it out, you know, drawing pictures or using your hands or whatever. So in this particular case, the way this torque is drawn is actually a positive internal torque. And the reason is, remember, just like with axial problems, we want to draw the internal torque vector so it points outward normal to cut. So that means my thumb would be the external torque vector, and then the way that that acts would be, you know, the curl of my right hand fingers. So that's in the same direction as the 800 Newton meter torque, okay? So this is a positive internal torque. So that means the angle of rotation, as I calculate here, is going to be in the positive direction or counterclockwise. The other way to think of it, okay, and this is probably maybe a little easier for a lot of folks. Try to think of it both ways. Let's just look at section CD. So I've drawn section CD here. And we know that on section C, we have the 800 Newton meter torque in that direction. And on face B, it's equal and opposite, right? That's what's going on in that section. So there we're drawing the internal torques on both faces. All right, so what's going to happen? Well, in this particular case, if we were to look at the rotation of face D relative to C, it's going to rotate in this direction, right? Which is in the opposite direction of the rotation of B relative to D. As you look at it down from point B, it's rotating in the clockwise, in the counterclockwise direction. So it's a counterclockwise rotation. So we can get that either by looking at the internal torque and visualizing on the shaft and seeing which way the two faces rotate, or we could be very careful about the sign convention, okay? But here we have a positive angle, and here we have a negative angle. So we have to be very careful because it's the difference of those, not the addition of those. And then finally, right, we're going to look at the last section, all right, where here, this is A, and this is a cut. So if we have the internal torque vector normal, that means that the positive sense of this internal torque should be this way. And this is the torque in section AC. Now, the external torque that's applied on that section is right here. It's the 200 Newton meters, and that's actually rotating in the same direction, correct? Did I do that the right way? Yeah. So that means the way this is drawn, that really torque AC goes in the opposite direction. Torque AC is really a negative 200 Newton meters. Okay? And if you use that into there, and obviously its length is 0.4 meters, we can get that the rotation of C relative to A is going to be minus 200 Newton meters times the length, which is 0.4 meters, over JG, which is the same stuff, right? The 0.251 to the minus 6 meters to the fourth, and the 80 to the ninth pascals, right? And so if we do that, hold on one second. Sorry, I'm responding to things in the middle of this. I shouldn't do this. Sorry, so let's do the numbers. Let's calculate the numbers. 200.
It's negative 0.0039.
That's it. Did I get the right numbers of zeros in there? Okay, I assume so. Thanks, I appreciate that. Okay, so that means, right, if it's a negative, that's a clockwise rotation, right? And again, if you don't see it that way, let's look at this section. So if we just draw here, that section A to C, right? If this is A and this is C, we have 200 Newton meters going that way. And then here we'd have bouncing at the internal torque of 200 Newton meters, right? And so that means that, wait, this is the one? Oh, wait, I'm sorry. Ah, I'm so stupid. All right, my apologies. If I use a right-handed rule, sorry, let's go back to here. If I use a right-handed rule, let's go back to here. If I use a right-handed rule, torque TAC should actually be going this way. And if that's the case, it's a positive torque. This is a positive. So this is a positive. And it's actually going counterclockwise. Okay, I'm sorry about that. And that makes sense too here, because if we go back to the picture I drew down here on the lower right of AC, right, the torque at face C is going in this direction. So that means it's going to rotate in the same direction, okay? Or if you're looking down from point B, that is a counterclockwise rotation, okay? So the total phi is going to be the sum of all those. So it's the minus 0.012 plus the, where's the other one? The 0.0199 plus the final 0.0039, and that gives me okay, that finally gives me the total rotation of B relative to A equal to negative 0.0118 radians, which is going to be a counterclockwise rotation. And let's just get this in degrees, okay? So that is 0.67, 0.68 degrees. All right. So that means since it's negative, right? Since it's negative, it's going to be counterclockwise looking down at B. All right. So looking down this direction, it's going to be rotating counterclockwise. So in other words, it's going to rotate in this direction. All right. So if this is face A and here is face B, don't know why I did that. So this is face B, right? So looking down X, it's going to rotate in the counterclockwise manner. So that means face B is going to rotate this way relative to face A. And the amount it's going to rotate is that 0.6, what did I say it was? 0.68 degrees.
Excuse me, sir. I think the number is actually positive. The angle.
Yeah, I thought positive.
Really? 0.012, that's a negative. 0.0199. Oh, you're right. Yeah, you're right. It's the same thing, but it's a positive. You're right. I'm sorry about that. Okay, so that means that actually it's going to go in the other direction, right? It's going to rotate that way, right? In a clockwise manner. So face B rotates 0.068 degrees clockwise relative to face A. Okay, does that make sense? I know the angles get a little bit tricky and it'll get even a little more complicated with when we do gears and whatnot, right? But yeah. Like I said, there's kind of two ways to do it again, and I think it's a good idea to try both because you can use one as a check on the other. The one approach is to treat it like the axial problem. Always draw the internal torque. So its torque vector, the right-handed torque vector is outward normal. Then, if it comes out positive or negative, that's going to tell you whether it's rotating in a clockwise or a counterclockwise manner. The other way to do it is once you know which direction the actual torque, arc vectors are going, you can draw them on the segment, and then you can determine which face is rotating relative to the other face, okay? And you just have to kind of be a little careful about the bookkeeping. All right, is there any questions on that? I'm going to stop there, okay? Because that is pretty much the end of class. All right, so fair enough. We'll see you Thursday, okay?
Professor, I do have a question about the last homework.
Okay.
I sent you an email, but if you can extend it or
Oh,
because of my
okay. Well, yeah. Let me see what I can do. Okay, I know I saw your email. You were, I'm trying to remember which one it was. You were having internet troubles, but you were here though, right? So Well, let me talk to you online. I know, I know, I know I have your email, okay? I just didn't respond to it because I was thinking about it, okay?
Thank you.
All right.
Professor, I also had a situation with the homework. For the cases of involving the material properties, I wasn't able to find it in the appendix. I'm using the online version. And I wasn't able
know.
to.
The online version does not have the numbers. So okay, so you know what? I need to, boy, I have an old text version. See, I don't have them either because I have the e-text. The e-text does not have the numbers of the material properties. Let me see if I can get the ones that the book reports and I can post them somewhere. I honestly
Okay.
don't. Okay.
Yeah, that was my only problem. I had to look them
Yeah.
up. That's why.
I'm
So
gonna assume they're the same. I've got like version, like this 5th edition. I'm assuming they haven't changed the properties. You know what I mean, right?
mhm.
So I'll do that. Okay.
Okay. Yeah.
I never have them either. You know. So
Will you post it on on an announcement, or like will they be like in
I don't know
in the
what's easy.
discussion?
Let me think about what to do. Maybe I'll just type it up and stick it on Blackboard. You know what I mean, right?
Yeah.
And people can use them as they need. All right. 'Cause,
All right.
yeah,
Then.
I honestly
Yeah.
don't know what to do there.
Yeah,
Seems like
that
a big
was my
mistake.
only
You
concern.
pay for the ebook. I don't know why they don't give you all the material in the book. I don't know. It's kind of frustrating. So. All right. It's probably. I bet you wouldn't be. I wouldn't be surprised if it's on their website. I'm going to go look. I wouldn't be shocked.
Okay.
All right.
Yeah.
Anything else?
Mm,
right.
Not really. No.
All right. Well, have a good one.